All right, so our final talk of this session is by Kate Lorenzen, and she's going to be talking about spectral properties of the exponential distance matrix.
Great. Yeah, thank you everyone for joining us here in our spectral session. So I'm going to be talking about spectral properties of the exponential distance matrix. So this started as a project for an RU group. So I kind of started working with Steve Butler, Liz Cooper, Erin Lee, and Zoe Shopik. So some of the results are available on archive, but I'll also be talking about a few new things here today. So just kind of the general area that this problem lives in is something called spectral graph theory. So spectral graph theory is the idea that we take a graph, and what we're going to do is we want to represent all of that graph structure with a particular matrix. And then once we have that matrix, we then want to look at the set of eigenvalues, which is called the spectrum of the graph with respect to the matrix, since the matrix is really just a representation of the graph. So some people who maybe it's been a while since they've seen some linear algebra, we have a matrix M and I multiply it by a vector x, such that it gets a scalar lambda times that vector x back. And then I'm going to call x my eigenvector and lambda my eigenvalue. So when we're talking about my eigenvalues, I'm talking about these values of lambda here. All right, so there's a lot of ways that we can represent a graph with a matrix. The first way that I want to talk about is with something called the distance matrix. So the distance matrix is going to have an ijth entry be the distance between vertex I and vertex j, where I want to think about my distance as my length of my shortest path. So here I have my graph, and I also have my distance matrix. So since vertex 1 is distance 1 away from vertex 2, since it only takes one edge to get there, I'm going to have a 1 in my 1, 2 entry. And since vertex 1 is distance 1 and 2 away from vertex 3, I'm going to have a 2 in my 1, 3 entry. Now, something I really like about the distance matrix is actually kind of the history of it, and one of the first times it was originally studied. So it was actually originally studied when they were trying to, way back in the day, set up the internet, and we were trying to figure out a way to have computers talk to each other, right? Be able to send messages to one another in an efficient manner. So the problem that the distance matrix was initially studied for was something called the addressing problem. And the addressing problem was really inspired by these Hamming codes on our cubic graphs, where if all of my nodes in my cubic graph are labeled with a binary string, such that two adjacent vertices are going to have exactly 1 bit different here. And what's really great about these Hamming codes, if I'm here, with a computer that's labeled 000, and I want to send a message to you, and you're at a computer labeled 101, I already know that there's going to be a length. The length of my path is going to be 2, since the difference, a number of bits, is going to be the distance between my 2 vertices. And in addition, I have in a really efficient way path that I know that I could be sending my message. So the general addressing problem was, okay, if we have a network of computers that's not just in a cube, right, but in any type of network or graph system, is there a way that we can address it so that we can get similar things to achieve while keeping our address length short, right? Because anything is possible if you allow infinite length. So this was solved by Graham and Pollock, and it did use the distance matrix and being able to decompose it in order to create an addressing system, where now each vertex is going to be labeled with 0, 1, or a don't care bit. And then the distance between 2 vertices is going to be the difference between the number of zeros and ones, where we don't care about the placeholders that are labeled D. And it actually turns out that the address length is going to be at most the maximum of the number of negative or positive eigenvalues of the distance matrix. So there we are, we're using the spectrum of the distance matrix in order to help solve this problem. So here I have a network here that has its appropriate addressing labels to be sending messages to and from the computers. So some other things that Graham and Pollock did when they initially were studying the distance matrix is they were really looking at inertia, right? Because their problem had the solution that your address labels had to be the max between the negative and positive eigenvalues. So they started to look at inertia, which is a tuple of the number of negative, 0, and positive eigenvalues. And they were able to find that for the complete graph. having n-1 negative eigenvalues, 0, 0 eigenvalues, and 1 positive eigenvalues, as well as all trees having the same inertia. Another thing they found, and probably I think one of the more kind of interesting results about the distance matrix, was they found that the determinant for all trees is just dependent on the number of vertices. It actually doesn't have to do with the structure of the graph, which is just, yeah, it's a very kind of interesting result that we have for the distance matrix. All right, so despite how cool I've been talking about despite how cool I've made the distance matrix sound so far, there are some limitations for it, especially when it comes to disconnected graphs. So you have this disconnected graph, and it wants to have a distance matrix too. But you might notice, though, the problem comes is, what do I put in my UV entry here? Well, it should be the distance, and so we would want the length of the shortest path, but there is no shortest path. And by definition, right, the distance between these two vertices is going to be infinity. And that's really not going to be helpful if we want to then have an infinite entry in our matrix, and then we want to be finding the spectrum. So one solution to this is the exponential distance matrix, which is going to be our matrix we're going to call DQ. And now I'm going to have the ijth entry be some variable q raised to the distance between vertex I and vertex j. So here I have my graph, and here I have its corresponding DQ matrix, where I have left q as a variable here. And so I have vertex 1 is distance 1, 2 away from vertex 3. And so I'm going to have q squared in my 1, 3 entry. Some things to note about this matrix. First, all of our diagonal entries are going to be 1, since anything raised to the 0th power is going to be 1. If I let q equal 1, I'm actually going to get the all ones matrix, which has really well-known spectrum. If I let q equal 0, I'm going to get the identity matrix for any graph, which also has well-known spectrum. And if I let my modulus of q be less than 1, and then this is actually going to be a well-defined matrix for disconnected graphs, because then q raised to the infinite power is going to be 0. So we took care of the problem that we wanted to solve there. So I'm going to be talking about some spectral properties of this particular matrix here today. And in particular, I'm going to be focusing when q is strictly between 0 and 1. There are other problems, some other things that we initially looked at where, q could be larger than 1 or negative. And I definitely think there's some kind of interesting results around those cases. But like I said, today I'm just going to be focusing on when q is between 0 and 1. So if I say something like for all q, I'm really meaning for all q between 0 and 1. All right. So one of my favorite things about working with this matrix is how it kind of behaves, especially, and I think that is most well shown while we are adding a leaf to a particular graph. So if I have this graph here and I want to add a pendant leaf vertex, how does that change within the matrix? So if I add my leaf u here to my graph, I have then my original graph on this upper block, and then I create this new column the way u is adjacent to everything else. Since u is going to be a distance 1 more away from all of the rest of the vertices from V4, I then want to add one distance to all my entries from V4. But since all my distances are the exponent, this actually comes to just multiplying that column of V4 by q. Now, what makes this really interesting is if we want to, like, say, take the determinant of when we have this graph and I've added my leaf vertex, I can rewrite that as taking my determinant of this block matrix, where again I have q times the column of my original DQ matrix here. And since I just want to take my determinant, I can use row and column operations to reduce this down to get zeros in that column. And then I can expand my determinant to get my determinant of my larger graph, where I've added a leaf vertex, in terms of the determinant of my smaller graph. And this is really great and useful, especially if we have a family of graphs that can be defined as iteratively adding leaves, which is the true family of tree graphs. So immediately from this result, the determinant of all trees for the DQ matrix falls out to be only dependent on q and n, the number of vertices. So this is actually very similar to the distance matrix result. All right, so some other things that have been worked on for this matrix. So this is with the kind of original RU group that I was mentoring. We completely classified the spectrum of the complete graph, path graph, and cycle graph. We found the spectrum of the join and the Cartesian product in terms of two kind of base graphs eigenvalues. And we also showed that almost all trees are not determined by their spectrum, meaning most trees, there's another tree that exists out there and they have the same set of eigenvalues, which really mirrors some results for other types of matrices. Some new things that I've been kind of working on that we're going to talk a little bit more about are results around inertia. So no longer completely classifying the spectrum, but instead kind of looking at like a larger trend of the spectrum when we look at inertia. Again, inertia is this tuple of the number of negative, 0, and positive eigenvalues. So I looked at 3 families of graphs, complete multipartites, trees, and unicyclic graphs. And we're just going to kind of focus a little bit more on unicyclic graphs. So a unicyclic graph is a graph that only has one cycle. One way we can kind of think about it is if I have a cycle initially, I can then iteratively be adding leaves onto this cycle to create my unicyclic graph, right? Because I'm never going to be adding an edge in between 2 vertices that are already in my cycle, because then I'm going to have more than one cycle. All right, and so the result I'm going to show is that the exponential distance matrix of the unicyclic graph has all positive inertia, or sorry, all positive eigenvalues. So my inertia is 0, 0, n. The proof of this, we're going to do it in 2 steps. The first one, we're going to show that if a graph has all positive eigenvalues, then by adding a leaf, all I'm going to do is going to be adding 1 positive eigenvalue. And then we'll show that just the cycle has all positive eigenvalues, right? And using this idea that a unicyclic graph can be thought of as a cycle, with then iteratively adding leaves, we get our result for unicyclic graphs. All right, so let's show number 1 first here. So if I have a graph and I have a leaf attached to it, I'm going to pull out some linear algebra arsenal and use some interlacing in order to show my results. So again, interlacing is we have a matrix, but if I have a sub matrix in that, I get that the 2 eigenvalues are going to interlace with each other. So if I assume that my small graph here, G, right, has all positive eigenvalues, then I'm going to get all but one of my graph with my added leaf is going to be all but one of my eigenvalues of my graph with my added leaf are going to be positive. In addition, I know the determinant of my graph with my leaf is equal to the product of all of my eigenvalues. We also showed before, right, that if I have a graph and I've added a leaf to it, that's going to equal to 1 minus q squared times the determinant of my original graph. Since I know my original graph has all positive eigenvalues and q is between 0 and 1, I get that this product is going to be greater than 0. Again, meaning that my determinant of my graph with my added leaf is greater than 0. So I have a product of a bunch of eigenvalues that is going to be positive, and I know all but one of them is positive, so I get that last eigenvalue is also going to be positive. Great. And so the next step is to show that our cycle graph has all positive eigenvalues. So the way I did this is from the previous work, we completely classified the spectrum of the cycle graph, and using properties of circular matrices, we can actually show that these are all going to be positive. But it's pretty technical, so I'm just going to hop right over that today. So that's how we would get the unicyclic graph has all positive eigenvalues. A very similar process for trees, right? Instead of the cycle being our base, we can just use the edge kind of as our base and use the same kind of induction step. The complete multipartite graphs are a little bit more interesting just because their inertia actually depends on the value of Q. And what do I mean by that? What I mean is that when Q is really close to 0, all of my eigenvalues are positive. And as Q increases, more and more of them become negative. And there's actually these very specific values of Q where some of my eigenvalues are going to be 0, and then they're going to be negative after that. This is kind of following from when we have our multipartite graph. We have eigenvalues of 3 types. The first type here, these are always going to be positive. And then I have my second 2, one are polynomial in Q, and the other's going to be roots of this polynomial. So graphing the roots of this polynomial to kind of see what is going on when I'm talking about most of my eigenvalues are moving. So here I have this polynomial. I have my roots here with my eigenvalues, and they're bounded by asymptotes. And the asymptotes actually happen to be my eigenvalues of the second type. And what happens is when q is equal to 0, all of my asymptotes are going to be over here on this side of my axis. And as q increases, what they're going to do is these asymptotes are just going to start to move and to become more and more negative. Whereas how I can get everything's going to be 0 at one point in time and then negative afterwards, except for this last eigenvalue, which we get to pick up from the trace. All right, so just kind of some concluding remarks here today, just some kind of further questions that we can have about the exponential distance matrix. The first would be, are there other families of graphs that have nice inertia or nice determinants out there? So, because we were kind of talking about several families today, the candidate I kind of think of is linear two trees or co-clique graphs. So instead of like iteratively adding leaves, we are iteratively adding cliques to a graph. So instead of attaching a vertex to just one other, we're attaching it to several other vertices. Another question that I have is, are there values of Q where the spectrum behaves differently? And this is a little bit more of a broader question just about the exponential distance matrix. From just some kind of data gathering, my idea is that Q equals 1/2 is just a different value of Q, where the spectrum is going to behave a bit differently. But I think this is definitely an interesting question, and it's still pretty wide open. So thank you all for your time, and I'd be happy to answer any questions.
All right, let's thank Kate. And any questions for her?
I have a question. So can you hear me? Yeah. So is there any relation of inertia of exponential distance matrix with the inertia of normal distance matrix?
So there is like, in terms of like the kind of the general proof sketch, but I mean, so for example, with the unicyclic and the trees, I mean, this is very different. The trees have mostly negative distance eigenvalues, and here for the exponential distance matrix, we have all positive eigenvalues. So not in terms of like the results, but yeah, thank you.
Okay. Thank you.
Any other questions?
Yes, I was wondering if there was any computations you've done, or if you have any intuition for what the characteristic polynomial of this matrix might look like, or if you have any sort of like Harari-Sachs theorem where you can expand it in terms of certain subgraphs.
Yeah, so so I'd say that with the kind of initial RU group, we did a little bit more of that. That's actually how we got the path graph, or sorry, so the path is, yeah, you can set up a kind of a recursion relationship. I mean, just because you have variable entries, things don't collapse down a lot nicer. But yeah, there's definitely some interesting things as far as having the subgraphs. I will say this matrix, when you leave the Q as a variable, I think it's really kind of nice to work with, because you know, especially compared to the distance matrix, you know, you really get to keep kind of like the distances as they are, and they don't combine together in kind of mysterious ways. Like, I don't know, it's just, when you keep Q as a variable, it's kind of easy to continue to pull apart and understand a lot of the structure of the graph from the variable polynomial, characteristic polynomial.
I have a question.
All right, well, yeah, go ahead.
Yeah, so for disconnected graphs also, you can define the concept of exponential distance matrix. Can we relate the like the spectrum of the components with the supergraph? Let's say your graph has 3 components. You can define the concept of exponential distance matrix for this disconnected graph. Can we connect the spectrum of this graph with its components?
All right, so I'm just gonna make sure I understand your question correctly. All right, So you're asking, can we connect to the spectrum of this graph to the distance spectrum of its components?
No, the exponential distance matrix of the components. You
Okay,
take a disconnected graph. Yeah.
I don't know if we've looked at that before. I will say though, from just working with this, I feel like the exponential distance matrix almost behaves more like the adjacency matrix, and that's more of just like a feeling than like I have lots of facts to prove that, than the distance matrix. Just in terms of what it preserves, and yeah, that's mostly it.
Okay. Yeah. Thank you.
All right,
I'd be happy to talk with you further. And during like the happy hour or later today.
Yeah. Sure. Thank you.
So we're out of time. Everyone's got to get over to see Steve's talk, but let's thank Kate one more time.